In this video, we are going to talk about heat change at constant volume. Now, heat change is constant volume is also, as we are going to derive this, would be equal to internal energy. So what do you mean by heat change at constant volume? So first law we have already learned. First law, the mathematical form is delta U equals to Q plus W. Now, if we consider only the pressure volume work, okay, this we have done in another video where we talked about how to connect work with the pressure and volume variable. And there we found that work done is equal to minus P delta V. Now, substituting this part of the work in the equation 1, that is the mathematical formula for the first law, we get the equation as delta U equals Q minus P delta V. Okay, so this is one important equation. Okay, now we are trying to derive an equation where the heat change is taking place at constant volume. So this is the equation that we got by putting the pressure volume work. Now, if the process is isochoric means constant volume, in that case, our delta V should turn out to be 0 because there is no change in volume. Okay, so if that is the case, equation 3 will reduce because this term will vanish. Okay, therefore, this equation will reduce to delta U equals Q. Or in other words, we can write that QV is equal to delta U. Now, I have used the subscript here because in order to indicate that this is the heat change happening at constant volume. That means isochoric process. Now, it's an important significance of an internal energy. Okay, so according to this expression, we can state that the heat evolved or absorbed, depending upon what is the process, taking place at a constant volume is a measure of change in internal energy, provided no work other than pressure volume work is considered. Now, here we have to remember that the work that we are considering here is the pressure volume work. Okay, and the pressure volume work is also referred to as the work of expansion. Okay, so in this particular understanding of this equation, it is mandatory that the work that we are considering here is only the pressure volume work. So in that case, any heat absorbed or evolved would be equal to the change in internal energy. Okay, so that is what do you mean by heat change at constant volume. So heat change at constant volume is nothing but equal to the change in internal energy. Let us look into a numerical here. So calculate the internal energy change produced when a gas expands isothermally against a constant external pressure of 1 atmosphere from this volume to this volume. If absorbs 640 joules of thermal energy from its surrounding. Okay, so let's analyze what are all the given facts. The first thing that you have to do is what are all the given facts. So here we are talking about a constant external pressure. So pressure volume work when we did, we gave the external pressure as Px. So Px is equal to 1 atmosphere is given. And the volume is increasing from 10 decimeter cube to 20 decimeter cube. So V1 be the initial volume to be 10 decimeter cube, V2 20 decimeter cube. Then the system absorbs heat, right? Thermal energy means heat. So absorbs heat, that is 650 kilojoule. So since it absorbs heat, it would be a positive value. So Q equals 650 joule. Okay. Now, what we have to calculate is calculate the change in internal energy. So that means we have to calculate delta U is what we have to calculate. Okay, so again, we are going to use the formula that we used just now. That means formula is basically the first law of thermodynamics, delta U is equal to Q plus P. Since we are considering here the pressure volume work, we can convert W into the PX format, PV format. So it would be Q minus PX delta V. Okay, so basically this part we know, that is 650 kilojoule. We have to calculate this part. Okay, so that is what I have separately calculated here. Now, this is joule, and we know that it's the SI unit of energy. So we have to make sure that the value that we get here should also be in joule. Okay, so doing that, as you can see here, W is equal to minus Px delta V. Now, Px is given in 1 atmosphere. Now, 1 atmosphere is not a SI unit, so we have to convert it into Pascal. Pascal is the SI unit, okay, which is basically Newton per meter squared. So this is a SI unit. So 1 atmosphere is equal to 101.325 kilopascal. Okay, so this is the conversion factor, which obviously you will be carrying the books, the unit books. So there they will have this conversion unit, but you can remember this. 1 atmosphere is equal to 101.325 kilopascal. Okay, and volume also you need to convert to the SI unit, since it's given in decimeter cube. We have to convert it into SI unit. SI unit is meter cube. Okay, so deci means it's 10 to the power of -1. So decimeter cube, that means 1 decimeter would be equal to 10 to the power of -1 meter. Okay, so decimeter cube means this cube. So it should be 10 into 10 to the power of -3 meter cube. Similarly, 20 into 10 to the power of -3 meter cube. Okay, so we are going to substitute these values here. Delta V is basically V2 minus V1. So V2 is this value, V1 is this value. Now, kilopascal, if we need to remove this kilo, you have to simply multiply by 1000. So 10 to the power of 3 here. Okay, now when you take the common factor out, 10 to the power of -3 is common, so you can take it out. So that will cancel out with the 10 to the power of 3. So what is left behind is 20 minus 10, that is 10 kilojoule. So it comes out to be minus 1013.25 joule. So that value, when you substitute here, you get the joule as the change in internal energy as minus 363.25 joule. So this is the way you're going to solve this particular problem. So thank you. Have a nice day.